All right, so now we're going to work on Chapter 3, Polynomial and Rational Functions. This is Section 3.6 out of our normal textbook, Zeros of Polynomial Functions. But we're also going to include Sections 3.3 out of the other book, and this is the real zeros of polynomials. And again, that page is in our section we have in our shell. So we're evaluating a polynomial using the remainder theorem rather than substituting a value in and simplifying. So that's what we're going to do today, part of the day. And so what happens is for the remainder theorem, if we have some polynomial f of x and we divide it by some x minus k, and we're going to use synthetic division because of that, then the remainder is going to be the value of f of k. So what does that mean? Well, let's try that. So we're going to find f of k for the given polynomial using the remainder theorem. All right, so we have 2. Okay, so we're going to take 2 and divide into that polynomial synthetically. And now remember, we have to have all the powers. So there's going to be a 0x cubed, and there's going to be a 0x. So we have 4, 3, 2, 1, nothing. So that's a 1, and then a 0, a -9, a 0, and a 14. So now we just follow through. So 2 times 1 is 2, and add, that's 2, that's 4, that's going to be a -5, so that's going to be a -10, and have -10, so that's going to be a -20, and add that, that's a -6. And so this is our remainder. Now it says if a polynomial is divided by that, then the remainder is the value of f of k. So that means f of 2 is equal to a -6. Okay, so that's what that means. Now, you could do hundreds of examples, and every time you divide or put in whatever value here, whatever your remainder is, that's what you're going to get there. Now, we can also use synthetic division to kind of factor, or at least partially factor, to a point where we can then factor on our own. Now, this is called the factor theorem, and k is a 0 of f of x if and only if our x minus k is a factor of f of x. So that means the remainder is 0 in synthetic division. So we want to see if this is going to be a factor, and then if it is, then we need to go ahead and find all the real zeros of that. So what we're going to have to do is we're going to have to use this and do our first division. Now remember, it's x minus k, and so in this case, k is 1. And we have 3, 2, 1, none, so that's going to be 2, -9, 13, -6. Bring down the 2, multiply, that's 2, add those, that's -7. That's going to be a -7. That's going to be a 6. That's going to be a +6, and that's going to be a 0. And so this then is a factor. Okay, so we have one factor, and so x is equal to 1 is one of the real zeros. Now, what does this give us? Well, this gives us 2x squared minus 7x plus 6. Okay. Now we could divide again, but we're going to have to figure out a factor to try. Now, if I look at this, I see something I think we can factor on our own without having to do any more synthetic division. So I'm going to say, well, it's going to be 2x and x. My factors of 6 are either 1 and 6 or 2 and 3. So I'm going to try the 2 and 3 first, because usually the ones that are closer together are the ones that we use. Now we can't put a 2 here, because otherwise if we could, that meant we could factor out a 2 here. So we have to put the 2 here. It means the 3 goes here. We know the larger is going to be a negative. And, well, actually, they're both going to be negative because we need a positive here. So that's going to be a negative, and that's going to be a negative. So now let's check and see if that is the correct factoring. 2x times x is 2x squared. Then we have -3, -4, that's a -7. -3 times -2 is +6. So this says then x equals 3/2, and this says x equals 2 are going to be the other two zeros of this polynomial. So we have x equals 3/2 and x equals 2. So those are our real zeros. Okay, and so that's all we had to do. We had to do that one synthetic division given that here. And then after that, I could see we could maybe factor it. So we tried factoring and we got it. We got the two other factors. And so we got our 3 zeros. And that should be how many we have, because that is our power. Okay. Now, all real zeros can be found on an interval, which can be found with Cauchy's bound theorem, okay? Now, with Cauchy's bound theorem, suppose we have the function f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 on down to a1x plus a0. And that's a polynomial of degree n, with n has to be greater than or equal to 1, okay? Now, what we're going to do and say let m be the largest of the numbers a0 over an, a1 over an, a2 over an, all the way down to an minus 1 over an. Okay, so then what's going to be is all real zeros of f of x, or of our original polynomial, lie in the interval between negative m plus 1 comma m plus 1. Okay. All right, so what does that mean? Well, first of all, we have to kind of think about what these all terms mean. So what we're gonna have to do is we're gonna have to see a0, that's gonna be the number term. So if we look at this one, a0 is a negative 32, okay? And so we're gonna take the absolute value of that over, and then we take over an. Well, an is the one with the highest term. Well, the highest term is a 1. So we take the absolute value of that. And so we'll write that down below, and that's going to be 32 over 1. Now, we're going to common, then we're going to a1, so that's the one on the x, so that's going to be a negative 40, so absolute value of negative 40 over 1 again. And so that's going to be 40. Now then we do a2, which is the next one. So we take the absolute value of a negative 12 over the absolute value of 1, and that's just going to give us 12. And then our final one is going to be the absolute value of 2 over the absolute value of 1, and that's going to be 2. Okay. Now, what does that tell us? Well, it says now the largest one of those, and well, which is the largest, 32, 40, 12, or 2, well, that's going to be 40. That's going to be our m. And then it's going to be on the interval from a minus m plus 1, so 40 plus 1 is negative 41, up to 40 plus 1, which is 41. So our interval is going to be between negative 41 and positive 41. And again, all we did is take each of these numbers divided by the highest one and have the absolute value of everything. So there's no negatives. And then the largest one is going to be m. And then our interval is just from minus the quantity m plus 1, comma m plus 1, and then brackets on both ends. And so that is going to be our interval. Okay. Now, while, Cauchy's theorem tells us where all the zeros will be, a list of possible zeros is obtained using something called the rational zeros theorem, okay? Now this says, suppose we have, again, some function f of x, we have a sub n, x to the n, a sub n minus 1, x to the n minus 1, on down to a0, and it's a polynomial of degree n, and n has to be, again, greater than or equal to 1, then all of these are going to be integers, okay? And so if r is a rational zero of f of x, then r is of the form p over q, where p is a factor of the constant term a naught, and q is a factor of the constant term a sub n. So kind of like what we had before, we took a naught over a n. We're kind of taking the same thing, except now we're calling it p over q. Okay, and so we're going to find all of those. And it's, again, plus and minus the p over the q. So we don't have to take absolute values. We just take p over q, and we take the plus version of it, and then we take the opposite of it. And so we're going to use that list of possible zeros of plus or minus p over q to try in synthetic division to actually find zeros. Okay, so this is to help us come up with a list that we can then do synthetic division on to find actual zeros. So these aren't the actual zeros. These are just a possible list of them. And so that's how we're going to find zeros to plug into when we, did synthetic division here, or, I think we did some here. What we were doing was we had to use some number. Well, what this thing is going to be a lot of plus p's over q's, and we just start trying, all the positives and then all the negatives, or start with all the negatives and then do all the positives. And that's how we're going to do our synthetic division to find the actual zeros. All right, so now the upper and lower bounds is going to be as follows. We're going to let f of x be a polynomial of some degree n plus greater than or equal to 1. So it has to be greater than that 1. Now, if c is greater than 0, is synthetically divided into f of x, and all the numbers in the final line of the division have the same sign. So, we're going to divide into, we're going to have c is some kind of number, and we get all positives basically here, all the same sign actually. I guess it didn't have to be positives, but they all have the same sign. They're either all plus or they're all minus, okay? Then c is going to be an upper bound for the real zeros of f of x. So that means we're going to have upper bound here. So there's going to be no real zero greater than that c value, whatever that c is. Now, if c is less than 0, and we do this synthetically division and find all the numbers in a line, alternate signs. So in this case, they go plus, minus, plus, minus, plus, or minus, plus, minus, plus, minus, plus, okay, alternating. Then it's going to be a lower bound for all the real zeros of f of x. So there's no real zero going to be less than that c, okay? Now note, if the number 0 occurs in the final line of the synthetic division, we can claim that as either a positive or negative as needed. So, if we came up here and there was a 0 here instead of a plus, we'll just circle that in. If that was the 0, well, we're going to call it a plus. Or maybe if we get a 0 in this place here, and we had plus, minus, 0, minus, plus, well, we would call that a plus, because that's how we can do that with zeros. So that's one of the things that's going to be kind of a little bit different, is we can use those zeros as either a positive or a negative. All right, so what we want to do now is use the rational zeros theorem to make a list of zeros. We're not going to test them. We're just going to make a list. Okay, so remember, we're going to find all the plus or minus p over q's. And p is the a0 and q is our a sub n. Okay, well, a sub n is 1. Okay, so that's 1. But this is, a n is 1 and a sub 0 is 32. And so what we need to do is we need to think about the factors of 32, because we need to have all the factors of p here, okay? So what are we going to have? Well, we're going to have 2 and 16, then we can have 2 and 8, and then we can have 2 and 4, and then 2 and 2. So we'll have all those possibilities, okay? And so what we're going to do now is we're going to say, okay, well, we'll have a sub 0. So we could have a 1, because, then this could be 1 and 2. So we could have 1 over 1, and it's going to be plus or minus. We can have 2 over 1, because that's one of these factors. We could have plus or minus 2 over 1. We could also have a 4. So we could have plus or minus 4 over 1. We could have an 8. So we could have plus or minus 8 over 1. We can have a 16, so a plus or minus 16 over 1. And we can have a 32, so plus or minus 32 over 1. So if you think about that, that's 2, 4, 6, 8, 10, 12 possible rational zeros that we're going to have to test. So that means we're going to have to test all of those with synthetic division if we actually had to find the zeros of this one, okay? And so, we would do synthetic division of a 1 and then a -1 and then a 2 and a -2 and a 4 and a -4 and a 8 and a -8 and a 16 and a -16 and a 32 and a -32 until we found them all. But remember, we can use that theorem here up here, that if we find one where it's all pluses or all minuses, we're either at the no greater 0 is going to be greater than this one, okay? So that will help us find that upper bound, and our lower bound is going to be if we have alternating signs. So, that's going to help once we have all these. If we get all, pluses, and we had, maybe at 4, then we know that's our upper bound. And so then we can only go down from there. We don't have to worry about, 8, 16, or 32 being positive. There's nothing going to be larger. And then maybe if we found that maybe a -2, we had plus, minus, plus, minus, plus, minus, or however many we need to have, then we know that's going to be our lower bound. And so then the rest of them are going to be somewhere between 4 and -2. We can't go beyond those limits. And so that's going to be something that's going to help us figure out, where our upper and lower bounds are. All right, so let's pause there and we'll come back with some more.